Just thought I'd give you a brief rundown of the set reset latch. What we have here is a relay, and with the relay what we have is a current which is flowing from this 5-volt source through this single pole, single throw switch into a coil. The coil is energized, and this little clapper over in here is being held down and being kept from making a connection up in there. What we're going to do here is we're going to interrupt the current. That will cause this clapper to move over to here. Current will then flow from here through this little conductor in through here, and then this coil will become energized. When that happens, this clapper will open. Current will cease to flow through here and will instead flow through the preferred circuit. Let's take a look and see how that works. And now we see the state has changed. We've now set the latch. Current goes through this upper circuit, energizes this coil, disconnecting that circuit. Let's go and set the latch again. We'll interrupt the current, and now we have created a storage device. It stores the state for as long as there is current. This is a 1-bit, that is 1 binary digit of storage, using a completely electromechanical switch. The basic idea is that you have 1 bit of what's called static RAM, although people don't call it that. If you have a large array of these relays, you could make as much static RAM as you like, as many bits as you want. But unfortunately, you'd need 2 relays for each bit. So if you wanted 1 kilobit of memory, you'd need 2048 relays, which is, well, a lot of relays. And of course, if you wanted 1 kilobyte of memory, you would need, well, 2048 times 8, or 16,536 relays, which is, well, a big honkin' pile of relays. But in any case, it is possible to fabricate the set reset switch with completely electromechanical devices. We can create our logic using other means. For example, we have some flip-flops that are available here under sequential logic flip-flops. Let's take a look at a clocked SR flip-flop. Here it is, the clocked SR flip-flop. We see the clock pulse coming in through here, and it gates 2 signals, the set and the reset signal. When clock is asserted high, the level will be gated into the SR latch. Because we have a clock, we call it a flip-flop. When it is unclocked, we're said to have a latch which constantly listens to the input. Here we're only listening to the input during the high level of the clock signal. Let's see if we can take a look at the output. Here's the set output and the reset output, and right now it's in a reset state. Let's see if we can change the state. We'll stimulate the input here, and sure enough, this has gone to a high state. And now we're going to do the same thing. We're going to reset the flip-flop, and now it's gone to a low state. Let's see what happens if we change the speed of the simulation. And you can see how things have propagated through. Let's do it again. So clearly it's holding its state. Let's do it again. It holds it for as long as power is applied, and this represents 1 bit of memory, done all with NAND gates. Could do the same thing with NOR gates, and in fact, you'll have the same effect. Thank you.